Good morning, everyone. The topic of my thesis is the optimization of boil of gas during emptying and filling of liquefied natural gas storage tanks. And the names of my professor supervisors are Professor Felisa Vesovic and Philippa Hutter. Now, I'll give you a general bird's eye view of my project. It deals with LNG, which is natural gas mostly methane cooled to its liquefied state at normal atmospheric pressure. And regardless of how we insulate the storage tanks, you always have heat ingress into the LNG storage tanks, and this causes a phenomenon called weathering. And weathering is the preferential vaporization of methane and nitrogen in the tank, and this changes the thermodynamic properties of the remaining LNG in the tank. Now, the vaporization, also called boil of gas, it needs to be continuously removed from the tank to maintain constant pressure. And a comprehensive dynamic model was used to simulate unloading and loading of the tank. And this model integrates the thermodynamic LNG vapor liquid non-equilibrium model, a heat transfer model, and the mass and energy balances that were modified in MATLAB. The objective of this project is to investigate weathering and optimize BOG during unloading and loading of LNG storage tanks, investigate the effect unloading an LNG tank has on meeting natural gas specifications before it's injected into the grid, investigate the effect of the initial liquid filling during unloading and loading of LNG natural tank, and to derive the analytical solution for zero BOG generation at critical pump flow rate during unloading. Now, this is a schematic of the basic design of an LNG receiving terminal. You see the ship. This is the ship that brings in the LNG to the regasification terminal and unloads it into the LNG tanks. And as the volume of LNG increases, it displaces the vapor, and the vapor is either sent back to the ship or it's compressed and sent to the natural gas grid. You have two pumps, and it has been designed in that way because of the heat dissipation generated by these pumps that will be shown later. And you have the pressure in the tanks. The first pump increases the pressure in the tank from atmospheric to 10 bar, and the second pump increases the pressure from 10 bar to 73 to 75 bar before it's injected into the gas grid. You have the LNG tank configuration, and you can see the heat ingresses into the tank from the liquid phase, heat ingress to the vapor phase, the heat ingress from the tank slab, also the heat ingress from the BOG into the LNG, and you can see the generation of BOG and unloading, and the terminology is used to derive the analytical solution and to modify the mass and energy balances in MATLAB. This is basically the mass and energy balances, and these equations were basically put into MATLAB to run the simulation successfully. You can see the mass balance here, and this is the energy balance. This is the heat transfer model, and this accounts for the non-equilibrium dynamic model of the vapor heat ingress from vapor to the LNG, and this accounts for the the heat dissipation from the LNG pumps. This is the analytical solution that was derived for the vaporization rate and for the critical pump flow at 0 kilogram BOG generation in from the simulation calculations. And you can see the calculations. You have the MATLAB calculation simulation and the analytical solution, and you can see that at at a high initial liquid filling, you see the percentage error is 3%, but as you decrease the initial liquid filling, the percentage error increases, and that's as a result of vapor thermal expansion that the analytical solution doesn't account for. Now, this is the BOG and vaporization rate sensitivity to pump flow during unloading. In figure 3a, At zero unloading, when you don't no unloading is occurring, the BOG generation is about 1,000 kilograms per hour. As you increase it to the critical pump flow 465, you have zero BOG. Exceeding this critical pump flow, you can see that the BOG is now negative, implying that you need to inject BOG into the tank to maintain isobaric conditions. In the vaporization rate, that is in figure 3b, as you increase the uh, unloading rate from 0 to 4,000, you can see that the vaporization rate increases. As one would might argue and say, as why should the vaporization rate increase when you're taking LNG out? Because heat ingress goes into the LNG, and a reduction in the LNG volume obviously should reduce um, the vaporization rate, and that will be explained in the next slide. Unloading at an unloading flow rate of 4,000 meters cube per hour, you can see that the heat ingress through the slab is 60 kilowatts. Heat ingress from the LNG pumps is well over 90 kilowatts, and heat ingress through the walls is 60 kilowatts. So you can see that heat ingress from the LNG dissipation, LNG pumps causes a significant amount of vaporization, which is almost 44% of the total heat ingress into LNG. During loading, you can see that as you increase the flow rates, the BOG increases, the vaporization rate also increases. And this is a result of the volume of LNG in the tank increasing. So the heat ingress into the LNG is also increasing. For the case of the BOG, at a given flow rate, as time progresses, the BOG decreases because the volume of vapor volume decreases, and this is as a result of vapor thermal expansion. And for the case of vaporization rate, for a given flow rate, as time progresses, the vaporization rate increases, and that's because the volume of LNG increases and the heat ingress increases through the surface area that is in contact with the LNG walls into the LNG. In the case of the BOG sensitivity to initial uh, uh, liquid filling during no pump, at a high initial liquid filling, the BOG generated is lower than at a case of a lower initial liquid filling. And as a result of vapor thermal expansion, the vapor volume is larger, is higher at a lower initial liquid filling, hereby causing uh, the surface area to increase, and the heat ingress into the surface increases the amount of BOG generated. In the case of vaporization rate, you see that a higher initial liquid filling generates a higher vaporization. In the case of unloading, a higher um, initial liquid filling has a lower BOG generation during unloading for the same reason as we seen earlier, and this is due to vapor thermal expansion. And you see that at a lower initial liquid filling, you can see that less BOG is needed, and that's because more BOG is in the tank due to vapor thermal expansion. So less BOG is needed to maintain this isobaric condition, whereas in the high liquid filling, you can see that more BOG is needed. For the case of vaporization rate, the higher the initial liquid filling, the higher the vaporization rate, and this is all happening during unloading. In the case of loading, you can see that the higher the initial liquid filling, the lower the BOG uh, generation, and that is because of the vapor thermal expansion as you as and displacement. Because at the lower initial liquid filling, and you flowing liquefied natural gas into the tank, you have a higher displacement of vapor coming out of the tank. And for the case of vaporization, you can see that a lower um, initial liquid filling has a lower vaporization rate. And that's because of a lower surface area for heat ingress into LNG. LNG composition sensitivity to unloading and loading. You can see that during unloading, the vaporization, the mole fraction of methane increases, and the mole fraction of nitrogen decreases, and this is all happening in the vapor BOG. The case of loading in figure C and D, during loading, the same occurs. The mole fraction of methane increases, and the mole fraction of nitrogen decreases. And this is because of the case of weathering, which is the preferential vaporization of methane and nitrogen. Nitrogen is lighter than methane, so it initially vaporizes, and then that's why there's a gradual decrease in the mole fraction of nitrogen. But you can see that it's well over 99% for the mole fraction for methane. And this is the LNG, the mole fraction of methane in the LNG is well over 96%, and in the gas, in the vapor, is well over 99.5%, and it meets the requirements. Same with nitrogen. Nitrogen is in the gas, in the vapor is almost zero, and in the liquid is about 0.035 mole fraction. So you can see that in conclusion, increasing the pump flow during unloading decreases BOG. However, the vaporization rates are significantly dependent on heat dissipation. BOG needs to be injected into the tank to maintain isobaric conditions when the critical pump flow is exceeded. Unloading and loading energy cans do not have a significant impact on energy composition. Weathering doesn't affect weathering. The initial liquid filling has a significant impact on BOG and vaporization rates, and vapor thermal expansion has a role to play, and this need will be investigated in future research. And an analytic solution for zero BOG creation at the critical point flow was presented, and this is very good because it helps engineers who don't have access to simulation packages to calculate critical point flows. Thank you.